Hello again, and welcome to the third session. In the previous session, Olaf presented the motivation of tasking framework in timeline. Also, he presented the basic features of tasking framework. This session will contain more details. I will present in the following slides the solution strategy, the API, activation model, execution model, and many more details. If I want to describe tasking framework in one sentence, I will say it is open source, event-driven, multi-threading, C++-based development library, and execution platform. These points help us to know what we may expect from tasking framework. Using tasking framework, you can develop an embedded system with static memory requirements. Also, a non-embedded system, like prototype. The application will be compatible then with POSIX-like operating system, like Linux and Artemis. However, Tasking Framework is not an operating system, neither a testing platform. Tasking Framework is currently available on GitHub, and it is licensed under the Apache License version 2. Tasking Framework is decomposed into API and platform. The API represents the entry point, while the platform is platform-specific code. The API is a set of classes, abstract classes, and few virtual methods. Your application, which consists of some or many functionalities or software components, can override the methods to implement this application. Then, Tasking Framework will use the platform-specific code that you will use to build the binaries, targeting Linux or Artemis. So let us start with the application programming interface, the API. To show the basic classes in the API or the basic elements of Tasking Framework, let us check a big example similar to the one that Olaf presented in the last session, slide number 2. Tasking Framework is implemented as a namespace tasking. In this example, the message will be realized by a class called channel. The computation block is realized by the class task. The input will be realized by input, and for periodic activation of the task, the time will be, or the period will be realized by a class called event. Before going further with Tasking Framework, it's good to understand the concept of the channel task model. The concept is to have a separation between data and functionality. The channel represents a data container where the task can handle this data, but the task object does not hold the data. Also, the channel represents an interface between two tasks, an interface between the input and the software, and also between the software and the output. This model improves their usability. It's also a typical model for onboard data handling. For instance, handling telemetry, where many processing components handle the received telemetry. Also, in distributed systems, some software components, or especially in the reconfigurable distributed system, where some software components need to be migrated from one computation node to another. The model of channel and a task. The model of channel and a task, where the channel is an interface, make the implementation in this case straightforward. We will show an example of reconfigurable system in the last session of this tutorial. Let's back to our example to show the sequence and the main methods that should be called. When the message arrived from the sensor, the driver or the main thread will call the push method from the channel class, which is in turn will notify the associated inputs by calling notify input. Notify input will try to activate the connected tasks. Because this task is waiting for another input, it will not be activated. But this task will be activated by calling activate. The tasking framework will signal a thread by calling perform to execute the pending instance of this task. This figure shows the sequence as a sequence diagram. If the input managed to activate the task, then the task will call the perform method to the scheduler object. The scheduler object is a container containing all the task channels and inputs in the application, and also it has some executors which are threads assigned to this scheduler. We will talk about this in the execution model, or we will talk about the execution model later in this session. Also later in this session, we will talk about the activation model. Because more than one executor can access the same channel, then we need to synchronize this access to protect the channel data or the data kept in this channel. I think you saw this slide before with Olaf in the previous session. To improve the security, the methods and variables that should not be modified by the software developer are implemented in these structures and then included as a private member in the related class. Let me now show an example to understand the channel task model much better. In this example, we have an input from the keyboard and we want to print on the terminal. So it's a simple task and we want to try to implement it using the channel task model or using the concept of tasking framework. In this example, which we call IO channel, and by the way you can find it in the example folder, we need first to read from the standard input from the keyboard. If the input is end, then we exit the application. Otherwise, we should append the new input with the last printed line and then print the new line to the standard output. If there is no new input within 5 seconds after the last print, we will remove the latest input from the line and print it again. And this time, wait only another 3 seconds and repeat it. If a new input comes, then we go again to 1 to append it and print the new line. We exit as explained with end. Now, let's think. We have read, which means we need a place or a container to keep this data, which means we need a channel. Let's call it input channel. Also, we have print. So we need another data container, another place to keep the data that will be printed on the terminal. Let's call it output channel. Also in the text, we find that there's seconds, there's time. So we need a timer or an event object. So we know now there is an event object. Now, what we have as a task? We have a task that appends the new input and print it out. Let's call it tar1. This task here will handle the data from read, which means it should be connected or associated with this input. But to connect with the input channel, we need an input object. Also, the task will print, so we need to connect it to the output channel. Another task is to remove the latest input and print the new line. Let's call it tau2. Tau2 will be activated after a time. So the input of tau2 is the time event, or the event object, the timer. And also it writes to the output, so it should be connected to the output channel. Now, one point is missing. Who will set up the timer? Let's tau1 set up the timer at the end of the execution, and also tau2 set up the timer for 3 seconds at the end of its execution. Now, we can tidy it up better and show it in this figure. This figure is exactly as shown before, where the keyboard will be connected to the input channel to notify the input of tau1, and tau1 will set up the timer after printing to the output. Tau2 will be activated from the timer, print to the output, and set up the timer. Because Tasking Framework has the platform-specific code, so we still need to say that this example is realized by Tasking Framework. Then we need a scheduling policy, for instance, FIFO, first in, first out, and executor. In this part of the session, we will talk about the activation model. The default activation model is the AND, in which the task will not be activated unless all the inputs are notified. When a channel notifies an input, the input tries to activate the task by calling activate. If the other inputs are not notified yet, the task will not be activated. The second model is the OR. To support this, a new flag was defined called final. If the final set is set, it's true, then the task will be activated immediately. So if we push to the channel and the channel notifies this input with final equal to true, the task will be activated immediately with no need or will not wait for the other two inputs. It's possible from those both and or to have some customized activation model in which some inputs with final set to false and one or more inputs the input or the flag final is set to true. This is useful when you have, for instance, some fault handling that you wait on the inputs, but then you define here a timer, and then when the timeout occurs and the inputs are not notified yet, then you need to take some reactions. Some tasks need to be activated periodically. That's possible in Tasking Framework using the class event, which can be considered as a timed channel. When a task is activated by this event object, then it can be activated periodically, where we provide the offset and the period to the event object. Therefore, the first activation will happen after the given offset, and the second one will happen after the offset plus the period, and so on. Also, it's possible to define relative time. Because relative time is less trivial than periodic activation, I will show it on a realistic example. Consider a task tau1 is executing and it needs to read from a sensor over the space wire. So at the end of the execution, the task sent a request to read from the sensor, and it sets the event object to a relative time, which is the time expected to receive the response from the sensor. From this point, exactly at the termination of the tau1, the relative time starts. When a relative time occurs, that will notify input 1, and because it's final, the task 2 will start executing. It's expected that the response comes, or the answer comes from the sensor before or during the execution. Task 2. So it's possible to define such one-time timer using the event class. We need to add more about the event class. In the code of the event class, we check if it will be executed immediately by checking shell fire, which means it's possible for some reason that you postpone the response. And this response represents two methods, on fire and push. For push, it's just the push from the channel class, where it will notify the input and activate the associated task. But for on fire, you can define some code should be executed when this timeout occurs, which means you may define this event as event handler with no associated task. You can have it standalone with some code in the on fire. If we have a task chain, then the default call semantic is asynchronous. So if the task chain is activated during the first execution, then the activated task, here's tau0, the first task in the task chain, will be executed according to its priority. In this example, we assume that tau0 has a higher priority than tau2. It's possible in tasking framework to implement a synchronous call by using the class group. So we add the tasks in the task chain to a one group, then the execution will be synchronous, such that the second activation of the task chain will start only after finishing the first execution. I would like to mention explicitly in this slide that the task model in tasking framework follows the directed acyclic graph with data dependencies. This example here is a realistic case study representing an optical navigation system from the Atom project. In this part of the talk, I would like to present the execution model in tasking framework. Each application in tasking framework should have at least one object of the scheduler class. The scheduler is a container or a frame containing all tasks, channels, and inputs in that application or a part of the application. Also, we should assign some threads to this scheduler object. We call them executors. Also, we should define a scheduling policy to this scheduler object, and the scheduler object will have two queues. Event queue to handle the events coming from timers, from the event objects, and also a task queue which contains the pending task to be executed. At the beginning, the main thread will create the executors. The executors or the executor will then wait on a conditional variable and will be in a waiting state. When a task is activated and there's a job pending in the task queue, then the scheduler object will send a signal to wake up the executor, and then the executor will become in a running state. The executor will check first if there's any pending event in the event queue to handle it. Then it checks the task queue to execute according to the priority or according to the scheduling policy we have to execute the pending job. After finishing executing the pending job, it will again check the event queue and check if there's then check if there's a pending task in the queue. If there is no pending event or pending task, it will go for waiting again. Now, in case we have more than one executor, let's say two executors, and while the first executor is executing a job or instance of task 0, task 1 is activated, and now there is a pending job of tau 1. The scheduler will signal the second executor to execute the pending job of task 1. In other words, we can say that we have a work-conserving scheduling, such that there is no idle thread. If there's no idle thread while there's a pending job. Also, there's a load balancing between the available executors. In Tasking Framework, we have 3 different scheduling policies to schedule the tasks in the task queue. First in, first out, FIFO, or last in, first out, or priority-based, which is a static priority non-preemptive scheduling policy. That's with respect to the tasking framework. Now, if we have more than one executor, then the tasks will be executed by any of these executors. In other words, we have a global scheduling with respect to the executor. If we consider the operating system, then the operating system will have its own scheduler. Then we have a hierarchy scheduling in this case. We said that we have a global scheduling in one scheduler object, such that each executor can execute any of the pending tasks in this scheduler object. But how then we can handle priorities? The application may have more than one scheduler object, let's say 4. We can assign priorities to the schedulers which will be scheduled using the operating system. In this case, we handle priority in group. So the tasks with a certain group of priority will be assigned to one scheduler object. Also, with this approach, we can fix the affinity of the executors to one core. So we may then have a global scheduling or a partition scheduling of the executors, which means of the tasks. In this slide, I will show or clarify how an executor handles an event in the event queue. When a timeout occurs in the event object, an event will be queued to the event queue. The executor, which checks first the event queue, will check if there's a pending event. If there are any, it will try to handle this event. Handling the event includes if the event is a periodic or it's coming from a periodic event object. It includes computing the next activation time. But what is this clock here and here? Clock is an interface to the timer. In Linux, it is a thread. So this thread will compute the next execution time and also will notify or signal an executor after queuing an event in the event queue. Because in your application you may have a lot of event objects, then the sorting will not be or the sorting will have a high overhead because you need to sort the events according to who occurs first. To handle this and to optimize the sorting of the event queue in case of multiple event objects, there is a class called periodic schedule to optimize the sorting in the event queue. As we mentioned earlier in this session, we have a platform-specific code. So for each new platform, we need to provide these 4 classes: the scheduler execution model, mutex, signaler, and the clock execution model. Those are, again, specific for the target platform. Tasking framework is supported with unit tests. Because the scheduling is a platform-specific implementation, we implemented a new scheduler called Scheduler Unit Tests. This new scheduler uses step function to simulate the scheduling implementation. In the test folder, there are some unit tests to test our API. We use the Google tests to write our unit tests, and in the main we simply run all tests. Let me now show the documentation of Tasking Framework. Tasking Framework is supported with 3 different kinds of documentation. First, it's a doc file. In the doc folder, you'll find a documentation on Tasking Framework, which explains what we showed in this tutorial, or similar to what we show in this tutorial. Also, we have inline comments. So each file in the Tasking Framework has enough inline comments describing the classes and the methods and the variables. Also, using Doxygen, you can build using make doc an HTML documentation using Doxygen, which will provide you with a nice tree and details about the classes and variables and methods. This session was too long, and I am pretty sure that you have many questions you want to ask. about these slides I presented and also some details or more details you want to know about Tasking Framework, you can join the live Q&A session and I will gladly answer all your questions. See you later.